I already debunked that. He lives close. Crow 777 or whoever the guy was that did that. He lives near an airport, and you can time the times that he takes his lunar wave photographs. You can time it to planes taking off. I got to
live next to an airport. Okay, you said Crow. I've debunked Crow. He lives next to an airport. So you can time the planes taking off. You just blab bullshit, bro. I'll rest.
The moon is waving. It's this.
Do you know where Crow lives, Sean? Sean, you led. Anyway, you led with he lives next to an airport. Do you know where he lives, Sean?
No, I don't know where he lives, but my
debunks that. He lives close. Crow 777 or whoever the guy was that did that. He lives near an airport, and you can time the times that he takes his lunar wave photographs.
Rests on you.
You can't answer the question.
The burden rests on you, Sean. Do you know he lives next to an airport?
No.
Okay.
Then don't lead with he lives near a fucking airport.
More than likely, he lives next to an airport. See, Brian has a heart.
So let's focus on the number 2 boxes. Above each number 2 box is a Polaris. So the middle number 2 box represents a guy standing directly underneath Polaris 90 degrees. The left number 2 box represents a guy 45 degrees at Polaris. So they all have their own Polarises. That's how it has to work on a globe. So if you have 2 guys standing 1 mile apart, then they're looking up at their own little spot in space at their own Polaris. Sean is going to complain that we have to move Polaris to make it work. Look what the globe has to do with Polaris to make it work. You can have 2 men on opposite sides of the Earth 1 degree below the equator simultaneously looking at Polaris on the horizon. I'm going to show you the ridiculous amount of refraction that requires, and he'll still probably complain about my refraction model. So if we just give him the benefit of the doubt and put Polaris at 1 light year away, there'd be 101 billion miles of refraction simultaneously happening on each side of his ball. That's the type of refraction the globe is dealing with. So I'm going to beg the question with Sean tonight, and I'm going to first show him their ridiculous proof of refraction, and then I'm going to show my model of refraction. So what I'm showing here are examples of real life refraction and not just baseless assertions. The guy has a direct line of sight, and he opens a warehouse door and lets a little cold air in, and he closes it, and we see the white light disappear first because it's the lowest, and then we see the green light disappear next, and we see the toys cut in half. Okay, these are real life examples of refraction with a little temperature manipulation. Okay, they claim that the light refracts downward, but every time we look at a laser side on, we see it bending upward. Okay, all the globe brings is lasers and sugar water, and that also proves our model, and I'm going over that later on. So we can match real world observations over direct line of sight observations at a couple hundred feet of little flat bodies of water. So I have modeled the way I believe it to work with refraction over a flat plane with a ratio as a function of distance, which I'm going to demonstrate. So until my opponent can show light refracting downwards, all of his claims are nothing more than baseless assertions.
Only happens in the atmosphere because the air is denser lower down, so you should see the light curve downwards, and we should, looking at this end, see more of Chicago from this end. So let's see what happens.
This is Mick West using sugar water in a fish tank with a laser to try and demonstrate refraction in their model because it doesn't work in reality. But watch all the great lengths he goes through to try and hide compression. Pay attention to the antenna on the biggest building.
So what do we see here? We see the same view of Toronto that we saw before.
It is magnified, of course, but it's not distorted in any way. The image is exactly the same. It's just bigger because we're looking through the water.
So I've got about
So we see the big building with the antenna obviously doesn't line up. The shadow on the bottom doesn't line up. The little leaf right above that doesn't line up. But look what he's done prior to filling up the right side with water. Look how much smaller the buildings are compared to the left side. So he's put in a lot of work doing this deception, and he's got a plate on the bottom that's curving, depicting Earth curve. And he literally has to change that to get away with changing the angle and the elevation of the camera. So watch this midfill edit. You'll see the shadow and the little leaf looking thing move and the background staying the same. This is a joke.
Course, but it's not distorted in any way. But it's not distorted in any way. The image is exact.
So all that work he put in to get the height of the building and the size of the building to line up after compression and magnification. Give me a break. So here they've added the sugar water, and look, he just proves refraction over a flat plane. Look, he lowers down. Remember that black rim down at the bottom represents the shoreline, and we lose resolution, but we still have line of sight because there's a black rim all the way around the fish tank. So we never lose line of sight, yet half the city's gone. Like, I don't know what he thinks he's proven, but I mean, granted, I did slow it down, but you know, this is just compression. Now look, see the lasers off to the side. I'll show it hits the side, so he moves it over to the middle to try and get it to bend around the ramp. I don't think it'll bend around the ramp because look, he tries to do it, and I stop it, and it just hits the ramp. And why don't you show us if it bends around the ramp? Okay, look, that's on the side. He gives us a side view, and I slowed this down, or it wouldn't be so easy to see. But look at the light shining, hitting beside the ramp. Are you kidding me? Why would he have to do that? Then next, he says with his own words, he's simulating a laser. It's coming in from the top, I think. But look, he's just proving refraction on a flat plane. Look, we lose resolution of the ground as the compression takes effect. We never lose sight of the light until we lose the line of sight. So, welcome to Flat Earth, Mick. All right, we're going to test 69 miles per degree on a flat plane. So, we're almost directly underneath Polaris. We put in 89 degrees. That puts us 1 degree away from it. And we put in 69.1 degree for our baseline distance. And let's see our height to Polaris. And what do we, whoa, 3958.7, the exact globe radius. So now we know how they determine their fake radius by using flat plane trigonometry and putting it to the center of their model. So, not a coincidence. So let's do twice 69.1, so 138.2 with 3958 height. And look, 2 degrees, 88 degrees. So still good. Let's try 3 degrees. So 207 miles baseline distance. And look, 87 degrees. Still good. Let's try 10 degrees. So 10 degrees is 691 miles. 3958 height. And look, 80 degrees. So 69 miles per degree, still holding firm. So 15 degrees. We put in 1036 with 3958 height and 75 degrees. Still good. So let's try 20 degrees. 1382 for our height. For our distance. 3958 for height and 70 degrees. So you have to go almost 1,500 miles before it's even off by 1 degree. So in that distance, anything could happen, but just all we need is a little refraction. So I made a formula. So if Sean asks for angles to Polaris on a flat plane again, just remind him of this. 90 minus A over 90 times D times point A minus 1/2 A, where A is the measured angle and D is the triangulated flat plane distance, and point A minus 1/2 A is the ratio of refraction. So this is all real measurements and real calculations, no fantastical radius and no arbitrary bullshit 7/6R. This is real measurements, real calculations. We're going to put it to the test. So in this example, we measure 30 degrees to Polaris. So 90 minus theta is 60 degrees. We put that in. We put in our flat plane triangulated height to Polaris, which was 3958, and we calculate. So our distance, or D, comes out to 2285.7, and our A is 60.
You caught me off guard. I didn't think you were actually going to have some numbers. That's great. Hold on. All right, what do you have? Go ahead.
Okay, there's what I think you're looking for is, let's see, 29 degrees, 40.5 north, 36, 57.0. That's got to be within a few miles.
That is certainly within the parameters.
Had a point. So we're going to go 90 minus 60, which was 30. So 30 over 90, which is 30 divided by 90, times our calculated distance, D, which was 2285.7, times point A, so times 0.30, minus 1/2 A, which is 15. Gives us 213.5. That's our refracted value. That's what we have to subtract from our calculated distance, from our triangulated distance. So we're going to take 2285.7, and we're going to subtract our refracted value of 213.5, and we get a total of 2072. We're going to divide that by 30 to see how many miles per degree we get, and I'll be dipped in shit. 69 miles per degree. So if you think my formula is crazy, this is the first thing that comes up when you Google the Haversine formula for great circle distances in navigation. And look, it begs the question with R. So you can't do nothing on the globe without a pre-assumed radius. Okay, but the main point in all this is that even if I could get my formula to work exactly perfect, that doesn't prove that that's the type of refraction that's going on. It's just math. It's just a model. I don't even think this model's right. It looks like it's using radians and depicting degrees, but anyway.
Here's a little known fact. Even though the moon is 1/4 the size of Earth, 2 Earths can fit in the biggest crater on the moon.